All right, we spent most of this unit looking at expressions and simplifying or factoring expressions. A lot of time looking at just numbers, devoid from particular expressions. But now we're shifting gears looking at some equations, right? So if we start with a few equations here, some simple ones you've seen before. Let's go for all four of these. Right. Go ahead and solve, I guess we can number those, all four of those equations, right? Even before I finish writing the next problem, you probably already came up with solutions for the previous ones, right? These are very straightforward one operation expressions. And to undo an operation, we use its inverse operation. So if I'm starting with x and then adding 2, to get back to x, I'm going to subtract 2. Well, if this other side started with 10, if I subtract 2 from the left, I have to subtract 2 from the right. Whether I write that across as part of the expression or write it underneath, it's the same idea here. X on the number line plus 2, and then backwards 2 gets me right back to x where I started. Right, so I'm at x. And then 10 minus 2 is 8. Over here, I'm starting with x minus 2. What's the inverse operation to subtraction? Right, addition. So if this side starts with 10, then I have to also add 2. Oops. To that side, if I start at x, back up by 2, and then move forward by 2, if I associate these two together, I get the identity for addition, which is 0, right? X plus 0, I'm right back to x where I started. So back to plain x here. I don't have to write x plus 0, but I can. 10 plus 2 is 12. X plus 0 is x, so I get x equals 12. Here I'm starting with multiplication. So how do I undo multiplication? With its inverse operation, division, right? If I start at x and I grow it to 2 times the size, whatever that x was, now it's been doubled. How do I get back to it? Well, I shrink it by a factor of 2, or I cut it in half. One of those halves is the x I started with, right? Division undoes multiplication. In an informal way of saying it, division is the inverse operation to multiplication. So if I divide this half by 2, I have to divide the other, not half, but this expression by 2, I have to divide the other expression by 2. So this gives me x times the multiplicative identity as opposed to the additive identity. And x times 1 is just x. 10 divided by 2 is 5. So there's my solution there. And then if I'm starting with x and I'm dividing by 2, right? We haven't really talked about fractions yet. So we're still kind of thinking about dividing by 2 and then multiplying by 2, taking x, cutting it in half. There's half of x, dividing by 2. And then I get 2 of those sections. Well, 2 halves of a whole is a whole, right? I have a whole x there. I want to clutter things up with my diagrams. So I'm back to plain x. The 10 is also being doubled because whatever we do to one side, we have to do to the other. And that gets me 20, right? Now for 3 and 4, we often write these in a slightly different way. When I have x divided by 2, I'll often write that as x over 2. When I say x times 2, I'll often write that as 2x. And until we learn more about fractions, it's a little out of place to show dividing by 2 and multiplying by 2 and seeing that these cancel or these cancel. When we're saying cancel, we really mean we can associate this 2 with a half. And when we get into fractions shortly, we'll explain that in a little more clear way. We can associate these 2 to get the identity, and the same way we can associate these 2 to get the identity, right? Division is not associative or commutative. I'm not taking 2 times 2 and then saying x divided by 4. I'm saying if I divide by 2 and then multiply by 2, those cancel each other out. Those inverse operations give me the identity for multiplication, right? Whereas if I multiply this by 2, that doesn't cancel anything out. If I divide this by 2, division's not the inverse operation to subtraction. That's not getting me any kind of identity, right? If I take this and just multiply by 0, well, 0 equals 0. That's not helpful. If I take this and multiply by 0, that means I have to multiply this by 0. 0 equals 0. That's not helpful, right? We're trying to get the identity. We're not using the 0 property anywhere. We're getting the multiplicative identity when we're multiplying or dividing, or we're getting the additive identity when adding or subtracting. So here's one operation expressions. What happens if we have more going on in our original problem, right? What if I've got maybe 2 variables on one side, just number 5, and then also a sum on the other side? How can I simplify this? Well, I can just do the operations here, right? I know what x plus x is. X plus x is 2x. And I know what 7 plus 3 is. 7 plus 3 is 10. So even though I had some arithmetic to do first, it really is just one operation. And then I can divide both sides by 2. X times 2 divided by 2 gives me plain x. And 10 divided by 2 is 5, right? I combine these terms to get 10. I combine these terms to get 2x, and then I could put the new operation to both sides. All right, let's do another one. Let's say I have, that's going to take up too much space. Let's move that down here. 3 times x minus 6 plus 9 times 2 minus x equals 10 minus 745 plus 745. Okay, why don't you go ahead and solve that one on your own? What, you're intimidated? No reason to be intimidated. This equal sign is just separating 2 expressions. Before I start bringing anything into the red, I have to do what I did for problem 5, right? I want to simplify this expression as much as I can to get something as close to this as possible. And then I'll start doing something to both sides, right? So really, this is simplifying an expression. I have 3 times, okay, a plus here. So here's one term plus this and then a minus. So I've got 3 terms here. So 3 times parentheses, I'm going to distribute 3 times x. Why don't you simplify this one on your own? Right? 3 times x is 3x. 3 times 6 is 18. That's a positive 3 minus, so that's minus. And then next term, 9 times 2 is 18, both positive, and then that's a plus there. And then minus x. I want to look to combine like terms, so I have an x term and another x term, so 3x minus x, that's 2x. Minus 18 plus 18, right? Well, we were just practicing how plus 2 minus 2 gives me the identity. Minus 2 plus 2 gets me the identity. Minus 18 plus 18 is the identity. So this expression simplifies to just 2x. Draw my big equal sign here, right? So remove this one. There you go. All right, now let's look at our expression 10 minus 745 plus 745. That's another additive inverse pair here. I just have 10, right? I hope none of you got into 745 minus 10. Okay, so that's negative 735, negative 735, plus 745. What's going on here? All right, 745 minus 735. And 0, 4 minus 3 is 1, 7 minus 7 is 0. What a waste of time, right? When I see, fix that there. When I see 3 terms here, I want to be intentional and wise about how I combine those terms. Definitely combining this pair first and then adding the 10 is going to be easier, right? So ultimately, I get 10 on this right side. 2x equals 10. X equals 5, right? I didn't even bother to write it. Divide this by 2, divide this by 2, getting x equals 5. And really, this is already showing how we can solve every equation, no matter how complicated. And we'll get more complicated than this shortly. We can solve any equation by following the same set of steps. So let's write down those steps. To solve any equation. What did we do first? Well, for 5 and 6, we had to simplify each expression before we could start dividing by 2 to both sides. And that's, in general, what we'll have to do, right? First, we simplify each expression independently. Right? This sounds similar to how to simplify an expression, right? To simplify an expression, we identify the terms, simplify each term within that expression independently, and then combine like terms. And that's how we simplified this expression. I had 3 terms here. I simplified this first expression, then simplified the second expression, then simplified the third expression. Then I combined those terms to get this single term, this monomial of 2x, right? But 2x is a simplified version of this left-hand side expression. It has absolutely nothing to do with 745, right? We're going to simplify each of these 2 expressions completely independent of the other expression. Once both expressions are fully simplified, then we will do what we started this video doing, which is introduce the same new operation to both expressions, right? All of this red ink is that second step. I had an x plus 2. I brought in, from out of nowhere, I just decided to put in a minus 2. But as long as I put a minus 2 on the left, I also have to put the minus 2 on the right. If I put a plus 2 on the left, I have to plus 2 on the right. If I put a divided by 2 on the left, and you divided by 2 on the right. Whatever I'm doing to one side, I'm doing to the other. So I'm introducing the same new operation, whether it's plus or minus or times or divided, to whatever expression is already there. Right? And this is key. Technically, I'm not adding 2 to 2. I'm not even adding 2 to negative 2. I'm adding 2 to this blue expression. or I'm subtracting 2 from this blue expression, or I'm dividing this whole blue expression by 2. That's going to become really important. That subtle distinction can be really important as we get to these more complicated equations. I'm not introducing the operation to just one part of the expression. I'm introducing it to the whole expression here, and the same new operation to this whole expression here. Once I have introduced that same new operation to both expressions, what did I do? Once I have this minus 2 here, what did I do? I simplified this left expression. And separate from that, I simplified this right expression. Right? Each time I put in that red ink, the next step is to perform whatever operations are there now to get the next line. Right? In other words, I'm going back to step 1, simplifying each expression. So our third step is to repeat this whole process until we arrive at our variable, not always x, right, but usually x, until we arrive at x is equal to some number. That will give us the value that if we use it for x, will make the original equation true. So let's look at another example where we can see this on the screen here. So let's work up to number 7. All right, let's say I have 2x equals x plus 7. Okay. If I just divide both sides by 2, that will give me an x by itself over here. Great. But this other side is going to give me a really ugly fraction. It's not even that I'm getting a fraction. I'm not getting x equals 7/2. I'm getting x is equal to that same value of x plus 7, then divided by 2. That is not a pretty picture. That does not give me a value for x. That's a dead end. I'm making things worse instead of making them better, right? We need to be strategic about what we do to both sides. Well, instead of getting rid of the 2, maybe I want to get rid of the 7. So the opposite, the inverse of adding 7 is to add its opposite, right? To subtract 7. Let's try to keep the color coding appropriate here. So I'll do my minus 7. And over on the right, I got x by itself, because x plus 7, then backwards 7, that's x plus 0, which is just x. But here, I don't have like terms. This isn't 2 minus 7, neither is it 2x minus 7x. I just get 2x minus 7. This new simplified blue version of the equation is really no better than the original black version of the equation, right? I'm subtracting 7 from the right expression. I have to subtract 7 from the left expression. If I don't have any like terms, that's no good. So what else can I do? Well, maybe instead of subtracting 7, I subtract the x. X minus x, 1x minus 0x, sorry, 1x minus 1x is 0x. 0 times x is 0, 0 plus 7 is 7, right? Instead of thinking of this as x moving forward 7 and moving backwards 7, I can think of it as 7 moving forwards x and moving backwards x. I don't need to know the value of x to know whatever number you start with. If you add and then subtract x, you're back where you started. Similarly, like terms here, I don't need to know the value of x to know that if I have 2 of something, I take one of them away, I've got one of those things left. And 1x is x. So we haven't checked any of our previous equations. Let's check this one. X is 7. Let's see if that works. 2 times 7 is 14. And over here I have x plus 7. So that's 7 plus 7. 7 plus 7 is 14. 14 is equal to 14. That's a true statement. So x equals 7 is my solution to that original equation, right? I simplified each expression. There was nothing to simplify. This was already as simplified as it could get. This was already as simplified as it could get. Introduce the same new operation to both expressions. I did that. And then I simplified this to 1x. I simplified this to 7. I have x equals a number. That's what I want. So I'm done. Let's try another one of these. Let's clear the ink. Okay, I guess we're on to number 8 now. Okay, simplify each expression independently. Can I simplify 2x plus 3? No. Can I simplify x plus 7? No. Right? Now, just like when we talked about simplifying expressions, our eyes need to be trained to see those pluses separating out the terms. When we're solving equations, our eyes need to be trained to see that this equal sign is bifurcating the whole situation here. I'm taking this 2x plus 3, that's on one side. Bifurcate's a fancy word for cut in half, right? This equal sign has to remain. Actually, I never draw that line. So many other videos draw the line. This equal sign is separating one expression from the other expression. No matter what I'm doing, I have to see what's on the left-hand side expression, what's on the right-hand side expression. Right? So this is sort of our classic standoff where I have an x term with a coefficient times my variable and a constant term. Nothing more to do to simplify the left-hand side. And the same thing, a variable term and a constant term on the right side. Right? So now we're going to introduce the same new operation. I have 4 choices. I can subtract 3 from this expression and this expression. I could subtract 7 from this expression and this expression. I could subtract 2x from this expression and this expression, or I could subtract 1x from this expression and this expression. Any of those 4 are perfectly legitimate. What I don't want to do is start dividing by 2 to try to cancel that 2, right? Unless 2 is a common factor here, I can factor it out and then cancel. And 2 is a common factor for these as well, so I can factor it out and then cancel. You never want to start with dividing, right? And once we get further into fractions, we'll talk about that strategy. For certain problems, it is useful, but most of the time, we're going to start moving terms, right? Personally, I like to move my x's all to the left first. So here I have an x term in the left-hand expression. That's what I want. Here I have an x term in the right-hand expression. I don't want that. So I'm going to subtract x. And since I see how the like terms line up, I'm going to go ahead and write it underneath instead of off to the side. So x minus x is 0. 0 plus 7 is 7. 2x minus x is x. Plus 3 is still there as part of my expression. Really, I have 3 terms here. I just lined them up vertically instead of horizontally. Okay? And now from the x plus 3 equals 7, it'd be foolish to subtract 7 from both sides, because that's going to give me the identity by itself over here. And x plus, well, 3 minus 7, that's negative 4. over here, right? That's not giving me x equals a number. That's giving me x plus another constant term equals the identity. Then I'm going to have to add 4 to both sides, right? Because adding 4 is the opposite of adding -4. X minus 4 plus 4 gets me back to x. 0 plus 4 is 4. That works. But what a pain in the butt, right? So let's erase all of that. If you want to write it down to contrast it, go ahead. But I'm just going to go ahead and back up. Try to back up here. So instead of subtracting 7, once I have my x plus a constant term on the left, I'm going to subtract that value. X plus 3 minus 3 gives me just plain x. 7 minus 3 gives me 4. And I'm done. I don't need this last equal sign. Right? And we can check that. 2 times 4 is 8. 8 plus 3 is 11. 4 plus 7 is also 11. So these two expressions do have the same value when x is 4. Okay, let's try just a couple more here. Clear the ink. Number 9. Let's get into, now let's just do one more. 3x plus 6. Oh no, I do want to do the other one. I'm sorry. 9x minus 4 equals 2x plus 17. Right? This one, again, is already in that simplified version. There's no need to do step 1 to start because they're already simplified. I have a constant term and a variable term, constant term and variable term. So try on your own, introducing the same new operation to both expressions. We want to move the terms first. So you have 4 choices. Which one do you want to do first? I'm going to stick with my own preferred strategy of moving my x's to the left. So I want to get rid of the positive 2x by subtracting 2x. So 9 minus 2 is 7 of those x's. 2 minus 2 is 0. 0 plus 17 is 17. Now I have my x term on the left. I don't want a constant term. So I want to keep 7x by itself. What's the opposite of subtracting 4? Adding 4. So there's my 7x minus 4 plus 4. There's plain 7x. 17, 18, 19, 20, 21. And now to undo that multiplication, I'm going to divide by 7. And x times 7 divided by 7, that gets me x. 21 divided by 7 is the whole number, 3. I'm introducing a new operation to both expressions. Then I simplify this expression. That gives me 7x minus 4. Then I introduce the plus 4 to both sides. I simplify that expression. It gives me 7x. Then I introduce divided by 7. I simplify that expression. It gives me x. Right? Same thing on the other side. Because I introduced negative 2x, I simplify this expression. It gives me 17. I introduce the plus 4. I simplify this expression. It gives me 21. I introduced the divided by 7. I simplify that. It gets me the number 3. Right? Now your solution will always be a whole number. We just haven't learned fractions yet. So we're not giving you problems that require fractions. So far, I haven't used much in the way of integers. All of our answers have been whole numbers. But let's see if I remember if this last problem will give me a whole number. So let's say Hope you can read my handwriting. Oops. Okay, can I squeeze that in there a bit? Whew, a lot to simplify here, right? So take your time, pause the video, simplify your left expression. That might take you a few steps. Then simplify your right expression. That'll take you a few steps. Once you get that full equation, watch the video again as I catch up to you. Once we all agree on the simplified version of the equation, then we'll pause the video again to finish solving it, right? Let's do that in 2 stages. All right, simplifying this left expression. I don't care at all about 11 and everything else there. I'm just looking here. I have parentheses, then times 5, so there's 1 term. There's a term, there's a term, there's a term. So I'm mostly looking at combining like terms, but first I have to distribute this 5. So 5 times 2x is 10x. 5 times 8 is 40. That 5 was positive. Positive times positive, there's positive 10x. Positive 5 times negative 8, that's giving me the negative 40. Positive 10x, negative 40. But then I also have this minus 7x, positive 6, and positive 3x here. So when I'm looking at like terms, 3x and 10x, both positives, that's 13x. And 13 minus 7, that's 6x. And then 6 and negative 40. 6 is going forwards, 40 is going backwards. So I'm getting the difference of 34, right? If I'm doing that off to the side, 40 minus 6, 10 minus 6 is 4, and then the 3 comes down. So 6x minus 34 is my left-hand side expression. So I'm going to move that over a little bit so it lines up a little more neatly. Okay. Now the right-hand side expression. Again, I have parentheses, 11 times this thing, there's 1 term. I guess I'm color coding, I'm keeping that in blue here. And then 6x and 90. So distribute here, 11 times 7, there's 77x. 11 times 2 is 22, so that's 22 in the tens place. Plus 6x plus 90. So I've got, now going to the green, 77x plus 6x. I'm going to pause here. A more advanced strategy. When we have a whole bunch of terms on the left and a whole bunch of terms on the right, sometimes you do see something pop out to you. If I have a plus 6x on the right and a plus 6x on the left, maybe I want to cancel that right away, right? Generally speaking, that's a fairly sophisticated eye to notice that and handle it well. So this general strategy, simplify this as much as we can. 77x plus 6x, 81 to 83, that's 83x. And then 220 is negative, 90 is positive. Let's do that off to the side. So they're opposite signs. We're going to find the difference. 0 minus 0 is 0. All right, so 22 minus 9. 12 minus 9 is 3. Carry that one. All right, 22 minus 10 is 12, so minus 9 is 13. But the negative one was the bigger one, so that's minus 130. Whew, all right. So you notice, once we've simplified everything, we get that same format we had for the last 2 problems. I have a constant term and a variable term being added, in this case subtracted. Over here, a variable term and a constant term as well, right? Now I can get my x's together and my constant terms together on the other side. So let's go ahead and move all my x terms to the left, just like usual. And here's the trouble some of you have when we just put it underneath, right? You try to do 6 minus 3 is 3. If we do the subtraction, right? 6 minus 3 is 3, and then I bring down the 8. Does that make sense? 6 minus 83 is 83. Or 6 minus 83 is negative 83. Neither of those can possibly be right. Even if I'm writing it underneath like this, I'm not literally doing the subtraction within the context of the problem. I'm not putting my subtraction bar there like I did over here. I'm just lining up my like terms to say negative 130 plus 83 minus 83, whether it's 83,000 or 83 halves, 83x and negative 83x are opposites. So that's going to add up to 0. 0 minus 130 is negative 130. Right? Technically, that minus sign is a plus negative. So when I say 0 plus negative 130, that's negative 130. This isn't minus 130, it's a negative number, negative 130. Okay. And then over here, 6 minus 83, well, opposite signs, I'm going to find the difference. The bigger number, as always, has to go up top. So it's 83 minus 6, borrow from the 8. 13 minus 6 is 7. So I get 77x. Oh, this is not calculated well. 77x minus 34. But it's not 77, it's negative 77 because my bigger number was negative, right? Those integer rules of understanding how integer addition and subtraction work are so important for solving equations. And so there's my negative 130 on this side. All right, so there, if we use our shortcut here, I had a plus 6x on the right and a plus 6x on the bottom, sorry, on the left. If I just canceled those 6 x's, I'd be left with a 77x on the right. But since I moved it to the left, it's a negative 77x on the left. Right, we didn't have to start with moving the 83. In fact, we could have moved the 6x instead. Subtract 6x from the left, subtract 6x from the right. That would give me 77x on the right. 77x minus 130, the negative 34 on the left. I could have added 34 as my first step. I could have added 130 as my first step, right? Any of those 4 terms, it's your choice. But I'm only going to show you one way because you've already spent long enough watching this video. You don't need to watch it 7 different versions of the same problem. But now that I have my x's on the left, the only reasonable choice to do next is to add 34 to both sides. Right? Trying to divide both sides by 77 is dumb. 34 is not a multiple of 77, right? Adding 130 to both sides, that's moving everything to the left. I don't want everything to the left. I want just my x term on the left. And then my non-x term on the right. So again, 130 is negative, my 34 is positive. They're going in opposite directions. So it's over here, 130 minus 34. 130 minus 30 is 100. So 100 minus 4, that's 96. And even though we haven't done fractions yet, we do know that whatever I'm multiplying, I have to use the inverse operation there, which is subtraction. Sorry, which is division. I think it's time to wrap this up here. So x times 77 divided by 77 is x times -1 divided by -1 back to positive, right? Negative divided by negative, those 2 negative ones cancel out the same way 7 cancels out, the same way 11 cancels out. We'll talk about that with reducing fractions. On the right expression, The factors of 77 are 7 and 11. Neither 7 nor 11 go evenly into 96, so I can't reduce my fraction. We'll talk about that later. But I do know I only have a single negative here on this term. So my answer is negative. And then because I just picked big numbers at random, I didn't plan out that this would be an integer. So we get x equals negative 99. Oh, 99, yikes. X equals negative 96/77. So that's a reminder to you when you're working on a test or a quiz or something, make sure what you're typing in is the answer that you mean for it to be. So double check that what you have written on your paper is what you're typing in on the screen, especially when it's kind of ugly here. Or if you're typing in a whole expression, make sure that all of those numbers are correct. A whole equation in that case. All right, now this is too ugly for me to plug in. It would take another 2 hours to evaluate this original black expression by plugging in negative 96/77, even if we already knew how to add, multiply, subtract, and divide fractions. So we'll leave it there. Our process is the important part. No matter how complicated our equations are, we're going to simplify each expression independently. Then we'll introduce the same new operation to both expressions, choosing wisely for what to introduce, right? Trying to get either the additive identity or the multiplicative identity, depending on where we're at. And then we keep going back and forth until we get to x equals a number. And that is how you solve any equation.